Everyone has been told the same story about Tesla, that the real breakthrough was the battery, that the range anxiety problem was the thing holding electric vehicles back, that once the batteries got good enough, the rest would follow. Engineers repeated it. Analysts repeated it. The automotive press repeated it for 15 years. And it sounded right, because it was mostly right, until it wasn't. Because what Tesla just put into production is not a battery innovation. It is not a range improvement. It is not a software update. It is a fundamental reimagining of the electric motor itself, the part everyone assumed was already solved, the part nobody was watching. And that is exactly the point. There is a question worth sitting with before we go any further. Tesla made the patents public. Any automaker in the world can download the technical drawings right now. Today, study every dimension, read every specification. So why does that not close the gap? Why can a company read the entire recipe and still not cook the dish? That answer does not come until you understand what the technology actually is at the material science level, and that is going to take a few minutes. Stay with it, because the payoff is real. To understand why this matters so much, you have to understand the problem that nobody was talking about loudly enough. Every electric motor that has ever been put into a production vehicle, from the earliest AC propulsion prototypes to every other manufacturer's best current product, shares the same physical constraint. The rotor, the spinning component at the heart of the motor that converts electrical energy into mechanical motion, is made from copper and steel alloys. Those materials have done the job. They have worked reliably for over a century. But they carry a limitation that is written into the physics of rotation itself. When a rotor spins, centrifugal force acts on every part of its mass simultaneously, and that force does not increase linearly with speed. It increases with the square of rotational velocity. What that means in practice is that as you push a conventional rotor toward higher and higher revolutions per minute, the outward force on the material becomes exponential. At a certain threshold, the copper and steel begin to deform. Microscopic at first, then measurable. The geometry of the rotor drifts. The precision of the air gap between the rotor and the stator degrades. Heat generation increases because the electromagnetic field is no longer operating at the design tolerance, and the whole system begins to lose efficiency at the exact moment you are demanding maximum output. That is why conventional electric motors have a power peak followed by a taper. Push them hard, and they give you a number. Push them harder, and they start giving you less than the number. The physics of the material sets the ceiling. Tesla's answer was to wrap the rotor in carbon fiber. Not coat it, wrap it, under tension, in a continuous layer of carbon fiber reinforced polymer at a precision that requires a machine Tesla had to build from scratch, because nothing on the market could do it. The carbon sleeve creates a compressive preload around the rotor structure that counters the centrifugal force trying to pull the material outward. The result is a rotor that can sustain rotational speeds beyond 20,000 revolutions per minute while maintaining its geometry, its electromagnetic precision, and its efficiency. The Model S Plaid, which uses 3 of these motors in a tri-motor configuration producing 1,020 horsepower total, goes from a standstill to 60 miles per hour in 1.99 seconds. Not on a drag strip with special preparation, as a production number, for a family sedan. The quarter mile falls in 9.2 seconds at 155 miles per hour. Numbers that until very recently existed only in Bugatti and Koenigsegg territory, machines that cost 10 to 20 times more and require specialized maintenance between uses. But the performance numbers, as dramatic as they are not actually the most important part of what the carbon sleeve does. Here is the part that the horsepower conversations tend to bury. Because the rotor structure remains stable at extreme speeds, the motor can sustain its maximum power output across the entire operating range. Older Tesla motors, good as they were, had a peak power point after which power began to taper. The Plaid's motors hold peak output all the way to the car's top speed. That is not just a track day advantage. That is an efficiency architecture. A motor that is not fighting its own material limitations at high speed is a motor that converts more electrical energy into motion and less into heat. Less heat means the cooling system works less. Less cooling work means less parasitic load on the battery. Less parasitic load means more range from the same charge. The carbon sleeve is simultaneously a performance solution and an efficiency solution, and that combination is what makes it structurally different from any previous motor design in production. Now, here is the thing that most of the coverage got wrong. The manufacturing challenge is not the carbon fiber itself. Carbon fiber is not exotic anymore. It is in bicycle frames, laptop cases, fishing rods. You can buy it at a hobby shop. The challenge is the differential thermal expansion problem, and it is brutal. Carbon fiber and copper expand and contract at different rates when temperature changes. If you simply wrap carbon around a copper rotor and run it, the thermal cycling of normal operation, heat up, cool down, heat up, cool down, will cause the sleeve to lose its compressive preload over time, or worse, cause it to crack or delaminate at operating temperature. Either outcome is catastrophic at 20,000 revolutions per minute. At that rotational speed, any structural failure in the rotor assembly does not fail gracefully. It fails violently. The solution Tesla arrived at requires the carbon fiber to be wound around the rotor under sufficient tension that the sleeve remains in compression even at the lowest operating temperature, accounting for the differential contraction between the two materials. Too little tension and it loosens. Too much tension and you risk crushing the magnets during the winding process. The wrapping has to be executed with micrometer level precision across the entire rotor surface, with the tension controlled continuously throughout the winding, while accounting for the angle of the fiber, the ambient temperature in the manufacturing environment, and the thermal state of the rotor itself. Tesla built a custom automated machine through Tesla Automation, their manufacturing engineering division, to execute this process. Every rotor is individually verified. This is not a process you can reverse engineer from reading a patent filing, because the patent describes what the result should be. It does not tell you how to build the machine that makes the result possible at scale. That machine exists in one place in the world, and it took years of iterative failure to develop. That is the moat, not the idea. The execution infrastructure behind the idea. This is the sentence that should change how you think about technology competition in this industry. Knowing the recipe is not the same as owning the kitchen, and Tesla owns a kitchen that took a decade to build. Elon Musk himself described the Plaid motor as arguably the most advanced motor on Earth outside of maybe a laboratory somewhere. That is not marketing language. That is an engineer acknowledging that the gap between laboratory proof of concept and mass production at the scale of tens of thousands of units per month is where most technology dies. The carbon sleeve rotor had existed in research contexts and in very limited high-performance industrial applications before Tesla. What Tesla did was figure out how to make it repeatedly, reliably, and at volume. That is the actual innovation. Mass producibility at that precision level is the thing no competitor has solved. Now look at the competitive landscape with that frame in mind. Lucid Motors built the Air Grand Touring Performance, a genuinely impressive machine with range figures the Plaid has not matched. The engineering inside that car is serious. But Lucid's total annual production volume is measured in the thousands, not the tens of thousands. Their financial situation has required ongoing capital raises. A company operating at that scale does not have the resources to develop and deploy a new manufacturing machine, refine its production process over multiple years of iteration, and bring the resulting component to market at volume. Lucid has engineering credibility. It does not have the industrial infrastructure to close this particular gap on any realistic near-term timeline. Rivian makes good trucks and SUVs with a loyal customer base and Amazon's backing. Their motor architecture is conventional. They are not in this race at the moment. Ford has the brand, the dealer network, the American consumer trust. But Ford has had to cut its EV production targets multiple times because the cost structure of building electric vehicles has not worked at the volume they projected. GM has committed nearly $35 billion to electrification, and the Ultium platform has produced real vehicles, but no moment of technical discontinuity. The Cadillac Lyriq is a good car. It is not a paradigm shift. And both Ford and GM are operating EV programs as departments inside companies that are still primarily building gasoline vehicles. The organizational incentives are divided. The capital allocation is divided. Tesla is not divided. Then there is BYD. This is the name that deserves the most serious attention because it is the only competitor operating at Tesla's scale. BYD overtook Tesla in total global electric vehicle sales. They build their own batteries, their own chips, many of their own key components. Their vertical integration is genuinely impressive, and their cost structure is lower than any American automaker. In 2024, BYD was selling over 2 million more electric vehicles globally than Tesla per year. That is not a small gap in volume. In the United States, however, BYD faces a different problem. Tariffs on Chinese-manufactured vehicles reached a level that effectively prices their cars out of the American market, and the brand does not yet carry the consumer recognition among American buyers in their 40s and 50s that translates into purchase decisions. Tesla holds approximately 43 to 46% of the American EV market. BYD's American share is not registering in the same conversation. For the foreseeable future, the American market, the most important market in terms of per-vehicle revenue, belongs to Tesla by a wide margin. What this means for the person thinking about buying an electric vehicle in the next 2 to 3 years is actually more important than the motor technology itself. The Plaid motor is currently deployed in the highest performance tier of Tesla's lineup. The question that matters for the broader market is whether carbon sleeve technology flows downward into higher volume models. Tesla's VP of Vehicle Engineering has confirmed that the architecture is real and the hardware has been discussed in the context of future performance variants of other models. But the Roadster gets it first. The next-generation Roadster, confirmed to be built at Gigafactory Texas, has been described as the proving ground for the most advanced version of this motor technology. Performance targets for that vehicle have been discussed publicly, and they surpass what the current Plaid delivers. When that car arrives, it will function as a demonstration that the technology can be pushed further, and that demonstration matters for what gets engineered into the vehicles below it in the lineup. Here is what the history of technology tells us about moments like this. A technical lead at the manufacturing level, meaning not just the design concept but the production infrastructure, is a different kind of advantage than a technical lead at the design level. A design lead can be copied, sometimes quickly. A manufacturing infrastructure lead cannot be copied quickly because it represents accumulated process knowledge, machine development, quality control iteration, and supply chain alignment that took years to build. When engineers at other companies download Tesla's patent filing and try to develop their own carbon sleeve manufacturing process, they are starting at zero on the manufacturing knowledge curve. Tesla is at the end of that curve. That gap does not close in 18 months, but the honest version of this analysis has to acknowledge what the technology does not solve. Motor performance does not determine who wins the EV market. The person deciding between a Model Y and a Ford Mustang Mach-E is not thinking about rotor construction methods. They are thinking about price, about charging, about software, about whether their existing relationship with a Ford dealer matters to them. The consumer who needs a truck and lives in a state with sparse charging infrastructure is making a decision that carbon fiber sleeve technology is not directly relevant to. Tesla's supercharger network, which opened to other manufacturers, was one of the most powerful competitive advantages in the industry, and it became less exclusive the moment that access was extended. Range anxiety is still real in large parts of the country where charging density is low, and the political uncertainty around EV purchase incentives, with the federal tax credit having been eliminated, creates a demand environment that is harder to predict than the technology roadmap. The honest answer to whether Tesla has permanently ended the competitive era in electric vehicles is that the question is framed wrong. What Tesla has done is establish a manufacturing barrier at the highest performance tier of the market that no competitor can currently replicate. Whether that barrier determines long-term market leadership depends on variables that motor technology does not control. Cost trajectories matter, policy decisions matter, consumer trust built over years of ownership experience matters, BYD's eventual path into the American market matters. The technology gap at the motor level is real, and it is significant. It is also one variable in a much larger equation. What you can say with confidence, based on the physics and the manufacturing reality, is this: the carbon sleeve rotor motor is not an incremental improvement. It is a structural change in what an electric motor can do, executed at production scale, with a manufacturing process that took years to develop and cannot be replicated from a patent filing. Every company in this industry now has to develop their answer to it, and most of them are starting from further behind than they publicly acknowledge. The recipe is public, the kitchen is not, and in manufacturing, the kitchen is everything. If this channel's approach to breaking down how technology actually works, not how the press release says it works, is the kind of analysis you want to keep watching, subscribe. This is what every video on this channel is built to do.